Hi everybody, I thought we'd have a quick look at surds and a bit of revision. So a surd is an expression that includes a square root, a cube root, or another root symbol. So over here I've got some examples. Root 2, cube root of x, the square root of a on 2, the 10th root of x squared, they're all surds. More specifically, we say that a surd's a precise representation of a number that can be written as a fraction. It's an irrational number. So if we use a surd, it gives us a precise answer, an exact answer, as opposed to a decimal representation. If we use a decimal representation, we tend to introduce rounding errors. Algebraically, they're similar to other algebraic terms. If we have a root a plus, an a root c plus another b root c's, we'll have a plus b root c's. So if we had 2 root 2's and added another 3 root 2's, we'd have 5 root 2's. If we have root a times root b, we end up with root a times b, so root 2 times root 3 is root 6. If we have the same root on itself, it's equal to 1, so root 2 on root 2 is equal to 1. Like with the normal fraction, if we have root a plus root b on root c, we can split it into 2 individual fractions, and that's quite useful to use in conjunction with the property above. And if we have root a on root b, it's equal to root a on b. Now many of these ideas are based in index laws. We know that root a is equal to a to the half, so a to the half times b to the half is equal to ab to the half. You know that a to the half on b to the half is equal to a on b to the half. And if we have a to the half times a to the half, that's equal to a to the 1, because a half times 2 is 1, which just gives us a. So we know that root a is all squared equals a, or root a times root a equals a. We need to be mindful that root of negative 1 does not exist. There's no two numbers that multiply. There's no number multiplied by itself that equals negative 1. So if we do have this situation, we know that we're going to have no solution. There is a branch of mathematics that deals with these solutions, but it's in higher maths and we won't be doing them. So simplifying surds is a large part of their use. Sometimes we'll have numbers that look like surds but can actually be rewritten as whole numbers. So root 100, 10 times 10 equals 100, the square root of 100 is 10. The cube root of 27 is 3. Finding situations like this requires us knowing our square and cube numbers and fourths and fifths and anything else that we're trying to use. So here's a bunch of them. So if we wanted the square root of 16, the answer would be 4, the square root of 64 would be 8, the cube root of 1000 would be 10. These numbers, generally speaking, come out of tables or extensions of your tables. So we commonly use these to simplify, and we'll break up terms to find square numbers and multiples of square numbers. So in the case of 2000, we know that 1000 is a square number. So we take the multiple of 2, put that under the cube root symbol, take the cube root of 1000, cube root of 1000 is 10, and we're left with the cube root of 2 to multiply it by. This, if we multiply it out, will give us the same answer as this. Similarly with root 2000 over 20, we'll simplify it to a fraction, end up with root 100, and we know that root 100 is just 10. Or root 8 divided times by root 18. We can rewrite root 8 as root 4 root 2. Root 4 is a square number, that will become 2. And root 18 will be root 9 root 2. 9 times 2 is 18. Root 9 is a square number, that will reduce to 3. We'll have 2 times root 2 times 3 times root 2. So that will give us, just rearranging it, 2 times 3 will give us 6. Root 2 root 2. Root 2 times root 2 is 2. By the properties we viewed above, 6 times 2 gives us 12, and there's our answer. Root 8 times root 18 is root 12. For those of you that are familiar with the simplification process, we can obviously do that in many less steps, but it's a good example of showing how you can do it without too much thinking involved. Now we use surds quite frequently in mathematics when we're doing Pythagoras problems. When we're finding the hypotenuse or solving for one of the sides, we'll take the square root of both sides. Now, when we take the square root of both sides, we end up with a positive and negative number. Because we're doing with lengths, we're going to ignore the negative solution. So x squared plus equals 3 squared plus 4 squared, Pythagoras' theorem. The hypotenuse is equal to sum of the squares of the other two sides. That gives us 9 plus 16, x squared equals 25. Take the square root of both sides, x equals plus or minus root 25, ignoring the negative solution. So the answer will be in fact 5. We might have the situation where we've got an equation in turning point form. We need to solve to find the x-intercepts. So we have x plus 5 all squared plus 5. We want to find out when y is 0. Subtract 5 from both sides. Take the square root of both sides. We instantly find that we have a square root of a negative number. If we have a square root of a negative number, we know there's no solution. In this case, there'd be no x-intercepts. Here's a case where we don't end up with a negative number on the right hand side. We take the square root of both sides, and this time we don't ignore the second solution because it has meaning. So take the square root of x plus 5 squared, we get x plus 5. Take the square root of 5, we get plus or minus root 5. Subtract 5 from both sides. Correct where you make an error. And we now know that in this case the roots would be at negative 5 plus root 5 and negative 5 take root 5. This being the line of symmetry and this being the distance from the line of symmetry. In the next example, rather than using completing the square, we're going to use null factor law to solve. So we have 4x squared take 5. We can notice that this can be rewritten as a difference of two squares. 4x squared, take the square root of that, you get 2x. Negative 5, take the square root of that, you get root 5. 2x squared and root 5 squared are both squares. Therefore, we can just instantly rewrite it as that. Equate both brackets to 0. If this is 0, the whole equation will be 0. That's the major principle of null factor law. Solve the two equations and you find out that x can be root 5 on 2 or negative root 5 on 2, which are the solutions for that equation. And would be the x-intercepts if that was the equation for a quadratic. We can simplify using square numbers. So root 98 would be root 49 times root 2. 2 times 49 gives us 98. Root 49 is a square number. Root 49 is actually 7. So that will simplify down to 7 root 2. We have root 29 on root 49. Well, that's not right. We have root 2a on root 4a, which is what it's supposed to be. I'll just make it a bit neater. I don't know if that's any better. Root 2a on root 4a, we can split the surds into root 2 on root 4 times root a on root a. 2 on 4 is a half. A on a is 1, so anything times 1 is itself, and that will simplify to 1 on root 2. Further examples. So let's have a look at counting like surds. We have a root 3 here and a root 3 here, a root 2 here and a root 2 here. I'm going to group them together. 2 plus 5 root 3s plus 3 take 1 root 2s, take away 1 root a. That'll give us 7 root 3s plus 2 root 2s, take 1 root a. If we're multiplying surds, order's not important, so I can just group together the bits that I need to. 2 root 5 times root 2 times 3 times 3 root 3. I put the root 3's together because I'm going to make that into 3 in a second. Put these together to try and multiply them together a little bit to make them neater. Root 2 times root 5 gave me root 10. I have 2 root 10's plus 3 times 3, which will give me 9. 9 times 2 will give me 18 root 10's. Or I could have written that as 18 root 5 root 2. Dividing surds, this is where that splitting of, you can split this one quite easily because it's only multiplying and dividing. So I split it to 5 on 10 and root 2 on root 6, and then changed root 6 into root 2 root 3. The root 2's will cancel. 5 on 10 will become a half. We'll be left with the root 3, so I'll have 1 times 1 is 1 on 2 root 3. Multiplying like surds, group the whole numbers together, group the surds together. 6 times 5 gave me 30. Root 2 times root 2 doesn't give me 4, it only gives me 2. So 6 times 5 times 2 will give me 30 times 2, which is 60. In the next example, 3 times 25 will give me root 75. I'm making the 25 because I know that's a square number and I can simplify that later. Plus 3 root 5 plus 2 root 3. Root 3 times 5 will give me 5 root 3 plus 3 root 5 plus 2 root 3. That's root 3, that's root 3. I'll have 5 plus 2 is 7 root 3s plus 3 root 5. Root 32 on 4 root 2. Root 32 is root 16 root 2. Root 16 is a square number which will become 4. We'll end up with 4 on 4 times root 2 on root 2. 1 times 1 will give me 1. And for our last example, I'll split this into 6 on 36 times a on root 2 root a. The root a's will cancel. The 6 on 36 will become a sixth, and we'll end up with 1 on 6 root 2. That's a bit of a reminder of what we've done with surds this term. I've put some example exercises on Connect. It's probably worth having a look at. Thanks everyone.